Welcome back to Impact Quantum, the podcast that explores the cutting edge of quantum computing, without requiring you to own a lab coat or a PhD. I'm Bailey, your dryly delightful British AI guide to all things quantum. And today, we're marking a milestone. This is episode 30 of season 3, which means we've officially hit quantum stability, or at the very least, podcasting coherence. Bravo, us. To celebrate, we've got an absolute treat, Vyam Patel, a master's student at the University of Waterloo, known by those in the know as Canada's answer to MIT. Vyam's here to share how he journeyed from machine learning to quantum algorithms, what makes error correction more thrilling than it sounds, and why foundational maths might be your best ally in this emerging field. He's brilliant, articulate, and suspiciously well-read for someone still in grad school. So grab your beverage of choice, settle in, and let's get quantumly curious with Vyam Patel.
Hello and welcome back to Impact Quantum, the podcast where we explore the emerging industry and field of quantum computing, where you don't really need to be a PhD or super into the physics side of things. You just need to be curious. And with me, as always, is the most curious, quantum curious person I know. I always got to make sure, Candace, that no, you're not the most curious person I know. You're the most quantum curious I know, because that one word changes the whole thing.
Yes, absolutely. Absolutely. And I'm super curious and I'm really excited. And every time we talk to someone new, no matter what they do, I learn something more. And
right.
I love
You get a new perspective.
I love it. I really, really do. And it just shows you how there's just so much space in this field for all kinds of folks. And
Absolutely.
I think that's great. So today we have Vyam Patel. He is a student at the University of Waterloo in Canada. They like to call that the MIT in Canada. So you understand that's smart school. And we're really excited to talk to him today. How are you today?
I'm doing good. Thanks for inviting me. Yeah, I look forward to our conversations.
Awesome. So we're talking in the virtual green room a bit. The thing that fascinates me, because you're still a student, you're obviously very early in your career, and you're already at Waterloo, right? The MIT of Canada, right? You could be anywhere, you could be studying anything, right? What made you pick quantum computing? Because I think that's really the question, right? That gets to the heart of the matter of, obviously you believe in the field. And so what made you pick quantum computing?
The short answer, which I'll start with, is that I find it's right at the intersection of mathematics, or I should say rather, applied math and computer science, or computational math in a way. So my bit of a background, I did my undergraduate. I started off as a computer science major, and then I added math as a second major. And I got very interested in the intersection of these two disciplines. So earlier in my undergrad, I was working and doing a lot of machine learning research, which was also yet another field which is at the intersection of two. But then near the end of my program, I found I was more attracted towards quantum computing because I found there were more opportunities to sort of work at this interdisciplinary area. So that was sort of the key motivation.
Okay, interesting. What in particular attracted you to quantum?
I should say at the first time when I heard about it, I think the whole claims of quantum advantage or quantum supremacy or the so-called exponential speedup, I think that attracted me the most. Again, having this computer science mindset, there were a lot of claims about you can solve something super fast in an exponentially faster way. And second thing was just during my undergrad, it's a very common curriculum in computer science courses. You take a course on theory of computation where you formally define what it means to compute. And we had one lecture on quantum computing, and they sort of described in how a lot of the conventional ways that we are used to thinking about computing they are just completely different when you move to the quantum computing side of things. So that also made me extremely curious about this new exciting field, and that's what I ended up going for my graduate school.
Oh, very cool.
I think it would be really interesting to ask you this, and I ask this every episode that we have, and I think it's great because we just get so many different answers. What is the biggest misconception about the industry that you're hearing that you would like to address?
I think the most common misconception that is often portrayed in communication in the news outlets quite a bit is this whole idea of you can first is that, oh, people simplify it a lot. So there's this notion of, oh, in quantum mechanics or in the quantum computing side of thing, you can just try all possible solutions to this problem that you're trying to solve in parallel. So you just solve for all possible solutions and then you pick the best one. That is simply just not true. There are just very, very specific instances where that might be true. But for the most case, we are not solving for all possible solutions at once. I think that's the most common misconception, which we hear quite often.
Okay. I again, I like the answer. It's different. It's not necessarily what I'd heard here before, and I like it. I think that's great. What's the most exciting risk you've taken with your career pursuing in quantum computing?
I would say that the field is in its nascent stage, even though there is so many big groups, research groups working in this area. It has not been concretely proven even from a theoretical standpoint that that using quantum computing for the problems that we are usually interested in is going to sort of give us a speed up. That's one part. The second part is the hardware is also not there yet. Companies have been telling it will be there in the next 5 years, but I think they've been always telling that, and we have made tons of progress, extremely great progress in the past 2 or 3 years. But again, these are the two big things. One is the theoretical guarantees on whether we will see a speed up, and second is the practical realization. So if these things don't pan out in, let's say, the next decade, then I would say that would be the big risk, short-term or medium-term risk, I would say, from a career perspective. Because at the end of the day, if you're looking to find a job, and if the field does not progress as some of the other fields did, then that would be sort of a biggest risk.
So how do you tell the difference between hype and true innovation? Because you have to admit, we're hearing new things every week. We're hearing new things every day sometimes. So how do you tell the difference?
I think I'm fortunately in a position where I have been surrounded at the University of Waterloo with some of the best researchers in this field. So I got the opportunity to take very advanced courses with them, and where the courses were designed in a way where they go back all the way to the fundamentals, and they would teach you a lot of these things from a rigorous standpoint. So when some big news come out, for me, I almost always just ignore it unless there is a link to the paper which is being published, because if I can see the results in the paper, I just cannot believe a news or a blog post. So that's sort of like the filter one for me. And once I find the papers, then if it's one of the big companies like Google or IBM, nowadays they are doing exceptionally good research. So you can get some good idea by reading the introduction and conclusion of the paper. Even though the paper might be 50 pages, you don't need to be an expert and read through all the 50 pages if you just get an idea by reading sort of the abstract, intro, and conclusion. So that would be like my first two filters and passes. And then if I do find something that aligns with what I think might be, oh, this could be interesting, then I'll just skim through the paper. So that's sort of my process. So I think the last part, skimming through the paper, that would require some technical background, which I was fortunate enough to have. But even if you are not necessarily an expert, I think my first filter is there like a technical paper which was released with this news announcement?
One of the things you mentioned, and I'm just curious, like, there's obviously a lot of papers getting published, right? How do you keep up, right? I mean, my hack for keeping up is I feed all the PDFs, and each research paper gets their own notebook LM, right? So I can kind of like have a podcast explainer. So while I'm driving the kids around, I can, well, maybe you don't have kids. So, but like, there's just so many demands on my attention and time. I find using AI, everyone's all freaked out about AI is going to make students cheat. I use AI to help me learn. And I would imagine that it's probably more widespread. Well, certainly we didn't really have AI when I was in university. Actually, that's not true. We had something called Prologue, which was this.
Yes.
Yeah, you're laughing. Yeah. Like, but I mean, cut us a break, like the ice age had just ended and, we just invented fire, right?
I love it. I love it.
I've used Prologue. I enjoyed my time, but that enjoyment lasted 3 months for the course that I was taking.
Yeah, that sounds about right. Yeah. I remember my final project to this day, and I'm like, that was an awful lot of work to parse the binary tree.
Yes. Yeah.
Sorry, go ahead. Go.
I was just gonna mention. I think for keeping up with the papers, I think so. My filter, well, again, because I work in I'm mostly interested in one or two parts of the quantum algorithm side of things. I have like this daily ritual. Just every morning with a coffee, I just go to Scite. Usually, there's less than 20 papers uploaded on the archive for QuantPH. Sometimes it might be 30, but usually I just skim through them. And if the topics are more algorithmic, I just read the abstract, intro, and conclusion. And from there, I can figure out if I need to dive a bit deep. I did try Notebook LM at some point when it first came out. Unfortunately, it did not work for me. It was just not accurate enough, even to give a high-level summary. I have not tried it since. This was a few months ago. I would say 6 to 8 months ago. So maybe things have changed quite a bit since then. But I think, for me, it's very easy and fast for me to just skim the abstract and then just know whether this is worth my time.
That's cool.
So is that how you keep up then, essentially on the industry trends and the new tech? Because if it has a white paper, then it's fairly substantial.
Yes, although I think because I still am like a grad student working in research, I think I would prefer if it was not necessarily a white paper, but like a proper technical paper that gets published in a peer-reviewed journal. So sort of that's being published in a journal obviously takes time, but usually pretty much everyone uploads their papers nowadays to arXiv. So that's the open source website where you can just go and filter by QuantPH, and all the papers published in. Even though the tag is supposed to be for quantum physics, I think nowadays it's mostly just filled with quantum computing related papers.
Right. And for those following at home, it's spelled, if you want to check this out, it's arXiv.
X.
Yeah.
Yes.
I don't want people searching around being like, I couldn't find that site you mentioned.
Yeah, Scite is also an alternative. Most papers from arXiv get posted to Scite. The nice thing about Scite is that you can write quick comments on if you have some questions about the new result. It could just be high level, and the authors themselves would usually respond. So that's a very quick way to sort of interact with them. So I usually use Scite as well. And there is a way where the most interesting papers, people will cite them, and they will just climb to the top of the sorting algorithm. So that's quite nice.
So what are some long-term goals that you have for what you want to do after you finish with grad school? Where do you want to situate yourself in the quantum ecosystem?
Or is it even too early to even ask that question?
Oh, that's fair.
Sorry, I cut you off.
I think for me, I've realized that I find two areas quite interesting. So broadly speaking, they are quantum algorithms and quantum error correction. Now, of course, like that's way too broad. So specifically, quantum algorithms for problems that arise in solving differential equations. So differential equations are one of the most common ways where a lot of these weather prediction is the most obvious example, but also nowadays there's a lot of simulation work going on and designing the aircraft, so simulating the flow around the aircraft wing. These are very computationally challenging problems. So my sort of interest through my research project went into this field quite a bit. And this is a fairly, I would say, new field on applying quantum computing to like a CFD or numerical PDEs in general. So that's one very specific area that I'm interested in. And the second being error correction. Again, error correction is a way too broad of a field. Where I see myself fitting in is sort of translating a lot of these academic papers to code implementations. I think that's a big missing part. That also helps me a lot accelerate my research, because every time a new idea comes in, but if I cannot quickly prototype and test it out, it's very hard to gauge whether this is applicable or not applicable. So I think I've gotten used and good at implementing a lot of these latest algorithm papers that come out. So that's a nice intersection where I would like to be in the short or medium term, I guess.
Okay.
Cool. So what do you think? What is do you have so you're a post-grad student, PhD, or somewhere else, or?
I'm a master's student currently in my
cool.
Second year.
Cool. So what areas do you think you're going to focus on in your research?
I think short term I would still be focusing on quantum, applying the quantum computing / quantum algorithms to problems, as I mentioned, in differential equations specifically. So I think that's the short term focus. And again, because it's a fairly new field, I think there is a lot to be done. And a lot of the conventional, because what we are trying to do right now, and when I say we, like a lot of researchers in this community, is we are used to thinking of solving these differential equations in a classical way. So we are just trying to map these classical ways of thinking to quantum computing. And then we've realized it does not always work out. In fact, it almost always does not work out. So we have to go back to the fundamentals. We have to rethink the way that we've been thinking about solving these problems classically, because on a quantum computer, even some simple things are not allowed, like nonlinear, simply computing like x squared on a classical computer. You just make two copies and multiply them together. On a quantum computer, it's not possible really. Like, I'm simplifying things, but that's sort of the idea. So this pushes you down to go back to the fundamentals, sometimes rethink the way of mapping your problem, and then bring it back to the quantum computing side of the things. So I think I enjoy that process a lot, and I think I would, in the short term, would like to continue working in that field if given the opportunity.
Now, this may be me being a software engineer by training and comp sci major by training, and I think that's really going to be a big growth area, right? The writing the code and at a very fundamental level is going. You're right. Like, it's going to be different, right? There are new ways to approach problems. You have to kind of drop your old way of thinking. I think the quote Yoda, where you have to unlearn what you've learned. So I think it's interesting because that means that there's going to be a lot of code that will need to be rewritten, right? And not like, hello world type stuff. I mean, core underlying algorithms for search and, all of those things are going to have to be recoded from the get-go. And, it's not exactly exciting work in a lot of ways, right? Bubble sort is not really the most fascinating algorithm in the world, but it's kind of where everybody starts. I think with quantum computing, I think we're going to have to revisit a lot of our underlying assumptions about computer science.
Yeah, that is true. I think, in fact, a big part of my research area was to there's this notion of block encoding. It's a fancy way of saying how do you encode classical information onto a quantum computer. Now, classical information is on quantum computer, you're only allowed very specific operations. Technically, they're called like unitary operations. Most of the classical operations that you would want to do are not unitary. So you have to make them unitary somehow, right? So a lot of these algorithms is they assume you know how to do that, and then the algorithm starts, then the paper starts. But for someone like me who's interested like in the next in applications in the next 5 to 10 years, I'm like, how do I do that first part, which is assumed to be true? So a big part of my my thesis and my research area was basically that. How do I encode this matrix, a classical matrix, onto a quantum computer? And turns out this is an unsolved problem. So I focus on very specific structured matrices that we see very commonly in numerical analysis or numerical mathematics. And and the approach that I took is like I had to go back, dig through these. Apparently, turns out you can automate a lot of this if the code is written in a way such that it identifies these repeating structures in the matrices. And the way I was able to do it is I had to go back to the old circuit design books from the second year of computer engineering or computer science, and like rethinking how to add two numbers together, and how to do these things on a quantum computer. So tracing back through all of the existing sort of literature, that's sort of where we are now. So like we are very early, but it's also exciting that that in a way that there's so many things that needs to be figured out. But it's also for me like an exciting path coming from like a computer science background as well.
That's true, because when you're in computer science, a lot of these basic fundamental problems have largely been solved, right?
Yeah.
Like bubble sort, right? I'll pick on bubble sort, right? But like with quantum computing, no. I mean, we're still early enough where they're naming things after the researchers who find them, right? So there's Shor's algorithm, Grover's algorithm, right? I don't know, like, maybe there'll be Patel's algorithm, right? Like, I mean, it's totally within, but in traditional computer science, I think those days are probably over. But in quantum computing science, like, I mean, I say that in jest, but it's totally possible, right? Like,
yes, yeah.
I think that's exciting, right? Like we really are in the frontier, and the frontier is exciting, but it's also kind of like, oh, no one's done these fundamental things yet,
Yeah, definitely. There's a lot more opportunities to sort of do. Like you could just come up with a completely different sort of background / mindset, and all of a sudden you just have just thought of something that no one else has before. And because we are so early in this field, it would be like, oh, you just stumble across a new algorithm, and maybe like eventually, as you mentioned, maybe it gets named after you.
Right. It's totally believable.
It just seems, it just seems like no. I'm just kind of amazed by the skill set you're talking about. With the computer science, and then you're talking about math, and then deep research. Like, what do you think are the necessary skill set to have when working on, like, for example, you were talking earlier about error correction. Like, I'm just kind of curious for people who have some of those skills, but maybe not all of those skills, how they could, if they could kind of break in and be involved. What kind of skill set do you think you really need?
I think it's really important to get the foundations strong. Luckily, the existing undergraduate curriculum is actually very well suited for this. Unfortunately, I would say that a lot of it is taught in a very, to give concrete examples, let's say undergraduate mathematics. So error correction, that's a great example. All undergraduate curriculum programs, they would go through these courses on linear algebra, abstract algebra, where they would cover group theory and rings and fields. Now, group theory and rings and fields, it's not necessarily like a new topic. This is, they also form the foundations of cryptography. And we have been using cryptography for like 6-7 decades now. Turns out the same foundations behind cryptography, the group theory and rings and fields, that's exactly what 90% of error correction is. Right, but this is and to me this was surprising because I took this course, an advanced course in my grad school. But when I took the course, I realized, oh, this is just 90% flashbacks to third year. But hey, it's been 3 years now, so I need to go back and get to know a lot of the fundamentals. But I would say like linear algebra would be sort of step 0. And luckily, that's covered in most of the undergraduate curriculums in STEM programs. So math, physics, computer science, engineering. And then if you want to get into some specific fields such as error correction, I think having a math background definitely helps. Working in algorithms, I think having somewhat of a computer science background could help. So yeah, and physics, again, if you're interested in error correction from a hardware side of things, physics background can also definitely help quite a bit as well. Okay. And yeah, and I would like to mention, like, before starting my grad school, I did not have any background in quantum computing at all. So it was a very new field for me as well. So yeah, all that I know, I've essentially just learned in the past 2-ish years, I would say. So yeah, like I come from a very common journey that many people in this community who are new, they also come from different backgrounds. They don't have a formal training in quantum computing, but I don't think that's an issue. I think that is okay.
No, that's a good point, right? This is a relatively new field. It's been around in one form or the other since the 90s, right? Candace, the little known fact, Candace's dad was an IBM researcher working on this in the 80s and 90s, right? So like this is not, in some ways it's not new, but in a lot of ways it's new to a lot of people, right? So you're going to find, I think, a lot of people, just like, when I was early in my career, there were not a lot of computer science people like in industry, right? Who had comp sci majors, right? A lot of them were people who had other degrees, be they science, even a couple of history majors, that had learned to code, right? As much as I hate saying that phrase because it was so abused. But they had kind of realized, like, I can, and I started my career on Wall Street, right? So there were a lot of also finance types that figured out that, hey, I could be a stockbroker. Yes, I will make a lot of money, but I will have an ulcer and a receding hairline by the time I'm 29, or I can kind of have a more leisurely pace and do coding for the write applications for the traders and things like that. So I also think that because this is a relatively new field, very very much in its infancy, you're going to see a lot of people that you're not going to have kids go to kids, right? You're not going to have people go to school and come out with a quantum a degree in quantum computer science just yet. Probably in about 10, 15 years, I think that'll be a thing, because it always starts off with grad school type programs, and then eventually it filters down into a thing. Yeah. But I'm very glad you said that, because that was my advice to my oldest child, is taking physics and calculus and math and things like that, because those are hard subjects, right? I mean, let's not like, those are hard subjects, and because it's hard, very few people are going to do it, right? And because very few people are doing it, market forces being what they are, there's not going to be a lot of people doing it. And our entire society, our entire civilization relies on a lot of the fundamentals of physics and mathematics. And it's alarming in a lot of ways that a lot of people don't know it, right? So, you will automatically be kind of whatever that looks like, right? I used to say, learn to code, kids, learn to code. But I think, the last, developments over the last, couple of years have really been like, yeah, maybe you should focus on more than just code, right?
Yeah, definitely. In fact, I think so. It's sort of like a two-sided coin in a way, because when I first got introduced to quantum computing, it was through one of those IBM summer schools, which I think was a great way to sort of bring a lot of people into this field. But to your point, I think there is a big misconception that you could just it's don't get me wrong, I think it's a great way to just start learning through being able to write these code to generate circuits, simulate them, but that's it. Like you all you're doing is just following a tutorial. And quantum computing, like, even though someone might make it sound that, oh, anyone can get in and it's very easy, all you need to do is basics of coding, that is simply not true. If you want to make any good progress, you would need to know the foundation, which, as you mentioned, math, physics, and even computer science. When I say computer science, I don't mean just coding, right? Like, we are in the era of GPT, so I don't think coding is that much required now. But I think what you do need is strong foundations in algorithms or like these, and these are covered in undergraduate curriculum. I think time has come that if this field as it progresses, I think more people will start hopefully focusing back on foundations, which I think is very important, because without that, you are essentially just writing code, but you don't really like know what you're doing in a way. So it becomes very hard to make progress in the field, especially when you want to work on the like state-of-the-art applications or even research in a way.
I think that's a good way to put it, because I think in popular culture, or we've confused computer science degrees with learn to code, right?
Yeah.
Those, I mean, it's a subset of a much larger thing, right? How computers actually operate, right? And I understand why it's easy to get those confused, but I think we do ourselves a disservice if we continue to do that, right? Because it'll be like, a lot of computer science major departments they're seeing shrinking enrollment, right? Because of the ChatGPT kind of situation. But there's a lot more to it, right? Like somebody still has to understand how networking works, right? How the packets work, right? One of my favorite phrases, Candace is probably sick of hearing it, right? Someone has to rack and stack them, right? And so, I mean, computer science, if listeners take nothing away from this other than that you're a smart guy, and Candace is sick of my jokes, it's that computer science is more than about coding, right? It's an entire academic discipline, heavily rooted in math, but kind of, branched off for very specific problems.
Yes.
So, yeah.
Let me ask you this. Has the idea of mentorship affected you in your path, your learning journey so far? Have you had a mentor that's really inspired you? Are you interested in being a mentor to other people? I'm curious about that.
100%. I think I have the usual story of you will hear this from most math majors. You had this one professor in their undergraduate. In my case, I was fortunate enough to have Professor Stephen Ryan from University of Saskatchewan. He taught me, I took vector calculus in my second year. Ever since I took that course with him, I just became, not just me, everyone else in the course as well, they just became fans. But lucky for me, I got to be more than fans, because I got a chance to do 2 summer research programs with him. I graded his vector calc for 2 years straight. And he was the one who sort of, he knew that what my backgrounds are and what my interests are. And I was this close when I got my grad school offers, because I was 50-50, but leaning more towards machine learning. He was the one who said, I've known you for the past 3 years. I think quantum computing would be the right field for you. And if you don't think you're convinced, do a summer research project with me. And he knew my background. He's just one of those people. And I did a research project with him over a summer, and I knew right there that, this is the field that I want to be. Without him, I don't think I would have been able to make it to grad school at Waterloo at all. And I've tried, I think I see him as inspiration, and also he was a great mentor. And I've been trying in different roles to sort of be a mentor to other students if I can. So in grad school, you get a chance to work as a TA. So that's one very common way to interact with first, second year students. But at Waterloo, they have a faculty of math, which is very unique to Waterloo. So it's not a department, it's a college of mathematics. So computer science is actually part of College of Mathematics at Waterloo. So that's very rare. So math is sort of one of the biggest strong areas at Waterloo. So in the College of Math, they have a program called Directed Reading Program and Directed Research Programs. And the idea there is grad students, masters, PhDs, and sometimes even postdoc, they act as mentors, and they can propose reading projects. And the undergraduates from year 1 to year 4, you will get paired with 1 or 2 students, and you have 4 months, essentially a term. And you will do readings together. You will assign the students or the readings, and they would read it. You would meet every week. and they would sort of ask questions. So this gives them the ability to learn something new, which is not part of their curriculum, but also it gives me the ability to sort of share some of my experiences and knowledge with them in a mentorship sort of role. So I think I've been, so this is the second term I'm doing it. I did that last term as well, where it was the same topic, getting first years or second year students into quantum computing. And then this term I'm doing it again. So I think that has definitely been a big part of my undergraduate / grad research curriculum.
Interesting.
Is there a book or a podcast or simply an idea that you've come across in the past year that has really changed the way you think about something or affected you in a way that you'd want to talk about?
Yes, I think the one book that comes to mind, it's a fairly famous book. It's called Quantum Computing Since Democritus. It is by Scott Aaronson, who is, no one is gonna, I think everyone would agree that he is one of the, if not the most smartest researchers in quantum algorithms, quantum complexity theory in the world, like period. He has worked under so many great people, and the work that he's been doing for the past 3 decades is just phenomenal. He maintains his own blog post where like a lot of the questions you asked during this conversation is about how do you know if a new news article is worth reading or not. I go to his blog post because he is one of those people who would just go and he would lay out the truth as it is, and he is someone that you can just trust without just blindly trust him. But he wrote this book in 2013, I believe, which was based on the lectures that he gave as a postdoc at University of Waterloo from 2007. But this book is written in a way which is at first pass when you read it, and if you try to do there are mini exercises. I could barely do that. These are not like math heavy exercises. These are very thought provoking exercises. So if you're not used to thinking the way that the book is written, it would be very hard. But this book sort of just opened my mind in a way. Like, what does it even mean to compute something? How and why quantum mechanics is so different than classical computing? And he takes an approach where you don't need to know any quantum mechanics. All you need to know is if you come from either a computer science background, that's the background he comes from, or if you come from a pure math background, you can still know everything all the foundations of quantum mechanics. So in this book, it's mostly not math. There's very less math, but it's written in an extremely thought-provoking way. And like every year, I try to come and read again, and I'm pretty sure I still don't understand all of it. But he talks about everything. He has chapters on what it means, the implications of quantum mechanics through like something like time travel. And this is not like the sci-fi time travel. This is like concrete formal implications. If time travel were true, can you solve things that a quantum computer cannot solve? And he has mathematical arguments to sort of go through this. So I would highly recommend that book, I think, to anyone, not only if they're interested in quantum computing, but in general, I would say.
No, that's a good point. There's a lot. I'm sorry.
I was just say, just for our readers again, say the name of the book again.
Yeah, it's Quantum Computing Since Democritus by Scott Aaronson. In fact, if you just Google Scott Aaronson blog, it will take you to the blog post. One of the things on the title of his blog post says, if you don't take anything from this blog post, take away this. Quantum computers do not solve everything in parallel. That's in like in the title of his blog post. It's like that's the biggest, because I think he also ran across the same thing. It's like many people have this misconception, so he's also out there trying to sort of do his part.
Go ahead, Frank.
Oh no, so Leah, there's a lot of interesting things that the retrocausality was something I heard about, which kind of implies, if not time travel, kind of a reverse flow to time. But I'm out of my depth beyond saying those sentences. but it's an interesting concept, right? Like the way we perceive what we call reality may not be the final word on how things actually work, right?
Yeah.
Which is very fascinating. Like I'm a philosopher at heart, so when I hear there's certainly aspects of a lot of these kind of quantum computing and kind of quantum physics things that really kind of bridge those worlds of hard science and kind of philosophy, right?
Yeah, and this book will definitely like take you to philosophy as well. So yeah, highly recommend.
Cool. I'm gonna order it.
What would you say is the most recent innovation that we've all heard about? If it's Willow, or I always pronounce it wrong, Frank. I pronounce it Majerno, which is the weight loss drug. And
yeah,
it's
that's
not
right. The weight loss drug. Yeah, Majorana.
Majorana, right?
I think it's named after somebody who's German or Spanish, so the J becomes a Y. Yeah.
Okay. So out of all, like, there's so much out there, right?
Yes.
What to you is the most exciting right now?
To me, I think there is this subset of error correcting codes known as QLDPC codes, quantum LDPC codes, which have very nice theoretical properties that has great implications on error correction, and it makes the resources required, because at a high level, the way error correction works is you have a lot of noisy qubits, and you essentially use like 100 noisy qubits to maybe simulate 2 or 3 perfect qubits. That's the rough idea of error correction. And I think QLDPC codes, the rate, which is the number of noisy qubits you need to simulate a certain number of logical qubits, that's quite high. So they are quite appealing to me. So IBM is sort of taking this approach for error correction. So that, to me, I think that's one of the most interesting areas that I'm looking. And QLDPC, again, LDPC codes are not new. These were first discovered in 1967, and they are used currently in 5G communication in our mobile devices. So now the quantum version of these LDPC codes are sort of one of the things that many people believe is state of the art.
Interesting. It's funny how it all comes back to a lot of research that's already been done for conventional computing, right? And correct me if I'm wrong, error correction was also a big deal in early hard drives as well as CD-ROMs, right? And DVDs, right? Because that's why if you scratch a CD up to a certain point, obviously, like it'll still solve it, right? And I remember there's error correction in a lot of things, like your credit card numbers. Right, there's like they have to match that to a thing. I don't know if that's for error correction or for other reasons, but even like barcodes, right? Barcodes that last little. I used to work on an e-commerce site, and like I remember, I forget how I got involved with, like, we needed to replicate the algorithm from what was originally written, and we needed to rewrite it in Perl of all things. And I remember that the last digit is actually a checksum, which is kind of it's a dollar store version of error correction that you're talking about.
So error correction, like classical error correction, is what enabled classical computers to function, basically. Like the field of error correction / compression / information theory, it started in, I think, 50s by Claude Shannon, but then pioneered by Richard Hamming and a lot of these classical error correcting scientists. But yeah, nowadays it's basically everywhere in all wireless communications, in something as simple as a CD-ROM in hard drives, even the transmission over the internet that has a certain notion of error correction inbuilt. So now a lot of these same principles have been translated over to quantum computing. And in fact, most of the codes that are being sort of researched now, they had their origins. They are classical codes at the end of the day, but they have been extended to work in this, because in the classical codes, you just have one sort of error, a 0 changes to a 1 or 1 changes to a 0. But on a quantum computing, you also have this phase, which is, you can have essentially a continuous phase along with the bit flipping between zeros and ones. So fancy way of saying you have more errors to correct. So your codes have to be much more complicated than just the classical error correcting codes. But that's a good starting point that most researchers build from.
Cool.
How would you describe what you do to a 10-year-old?
Okay. Yeah, I think to a 10-year-old, they have probably heard that weather prediction is important, or at least heard of predicting weather. So I would say, yeah, I work on designing ways that could help accelerate the process of weather prediction, whether it be more faster or more accurate. And the way I do it is using quantum computers. I think it should work.
I appreciate that. Thank you.
How would you explain this to? How would you explain quantum computing to someone who is looking to invest in these companies?
Oh,
I'm just curious. Not like you're pitching
Yeah.
them, but like let's just say you had a friend who's a venture capital and over coffee is like, hey, I'm in here about this quantum computing thing. What's the deal? Is it a thing? Is it not a thing? When will it be a thing? I know the when will it be a thing is a very controversial question, but needlessly controversial in my opinion, but it is what it is.
Yeah, I think from an investing point of view, it would most likely come back to the whole who gets there. Well, there are two questions. One is who gets there first.
Right.
But the second is, as of now, pretty much all companies are taking a different route at the hardware level. Someone is doing superconducting, Microsoft is doing topological qubits. Then we have ion trapped. So everyone is sort of trying different architectures. So the question becomes like, yeah, it's not just about who gets there first, but it's also about once you get there, are you able to scale it up such that you can make bigger and bigger computers? Because that's what we need at the end of the day to make it useful for the applications that we have in mind. So yeah, I think it would come down to can one identify like from a technical point of view, which one of these architectures are sort of the most appealing and they have the most promising future. I think to me that's what it comes down to.
And correct me if I'm wrong, but also each type of hardware is ideal for certain types of problems. And I think one of the temptations is because electronics, silicon substrate and all that has kind of become the dominant form of computing and conventional or classical computing. Do you think it'll ever collapse into one type of hardware in the future? Not anytime soon, or do you think it'll always be kind of like, somebody gave me the example of it's a bit like car engines, right? Like, there's diesel, there's gasoline, and there's electric, right? And yeah, there are some other things like fuel cell and all that, but most people have a gasoline, some people have diesel and electric, right? But ultimately, no one, while one does dominate, it never like fell into like one size fits all.
Yeah, I don't think it will ever reach that point where it's just one type of architecture is going to dominate and everyone else is just gonna it's just going to follow that path. I think each hardware architecture has its own pros and cons as usual. So I think it would still be sort of we would get a whole suite of different architectures. Maybe one architecture is more suited towards a particular applications or particular types of problem, and then some other application might have some other properties. So I think, yeah, I would imagine it. I don't think that it would just all collapse down to a single architecture.
Interesting. Where can folks find out more about you, your research, and what you're up to?
Yeah, I think the easiest way would probably be LinkedIn. I do plan on starting my own website pretty soon after I graduate. I think what I would like to do is start a technical blog, but this would not be a short blog. This would be a detailed blog that you would need to sit down for 2 and 3 hours. But if you do, you can avoid reading these 30, 40-page papers, because I think in my research, I had to read so many papers, and then after a point, you realize that, oh, this could have been explained in a much more simpler way. So I
Right.
think that's my goal, to write things in a way such that an undergrad with a STEM background can get it. So yeah, I think LinkedIn would be a short-term sort of way to connect. But I think eventually, in the next few months, I will start my own website. So I'm hoping that I can get more people engaged there.
Mm-hmm. Very cool.
That's perfect. Honestly, I've already ordered the book on Amazon that
Yeah.
that we spoke of. I think that sounds absolutely fascinating, and I really appreciate hearing, your perspective, from the graduate school level, to see kind of you're jumping off into this whole realm, and what do you care about, what's exciting, where do you want to go with it. And I appreciate you sharing your journey and your opinions with us today.
And I picked it up on Kindle
There you go.
Nice.
because I can get it like now.
Yeah.
And we'll make sure we put a link in the show notes, and we'll let our AI finish the show.
And that, dear listeners, wraps up episode 30 of season 3. Can you believe we've made it this far? Without collapsing into quantum decoherence. A huge thank you to Vyam Patel for joining us and proving that not all quantum researchers speak exclusively in equations. Whether you're here for the maths, the metaphysics, or just trying to sound clever at parties, we hope today's episode helped you inch closer to quantum enlightenment. If you enjoyed this conversation, and frankly, if you didn't, I'd question your taste in podcasts. Make sure to follow, rate, and review Impact Quantum wherever you get your audio fix. Until next time, keep your states superposed, your entanglements professional. And remember, in quantum computing, as in life, it's all about finding the right algorithm. Cheerio.